Okay, so going from, well, Central California to Southern California, another citizen monitoring group that relies sort of heavily on volunteer, but also has a professional staff, and one of those staff members is giving a presentation, Catherine Peace from Hilda Bay in Malibu, and she's going to be talking about her 12-year assessment and condition report.
Okay, thank you, Jim, for the introduction, and I'm happy to be here. So today I'm going to talk a little bit about the biological health of the Malibu Creek watershed. And so like Jim said, I'm from Hilda Bay. So for those of you who aren't familiar with our organization, we're a nonprofit environmental organization. And our mission is to make Southern California's coastal waters and watersheds safe, clean, and healthy. And we do that using a combination of science, education, community outreach, and advocacy to achieve our mission. So just to be clear, we're working mainly in the Santa Monica Bay. However, some of our policy work extends sort of statewide as well as nationwide. So we're working in the Santa Monica Bay. So let's see. So I think probably most of you guys know this, but we have downtown LA here. This is the Santa Monica Bay, so it's basically extending from Malibu down to the PV Peninsula. So the Stream Team Monitoring Program, this program began in 1998. It's a citizen science program, like Jim was saying. So we kind of originally started the program, I wasn't there, but the original goals were to determine and promote the environmental health of the Malibu Creek watershed. And we do that through collection of this sort of high quality, really usable data. We also do it through monitoring the stream and water quality conditions, and as well as doing actual hands-on restoration work of stream and riparian habitats. And then we use this data to inform local and statewide policy action related to streams. So just kind of an overview of the Stream Team program, some stats. So since 1998, we've had over 6,000 volunteers involved in our program, whether it's through the monitoring or also through the restoration events. And then so cumulatively, we've spent over 40,000 hours in the watershed from staff and volunteers. We have about 100 active volunteers now, and last year they donated about 600 hours of their time. So it's a really great resource that we depend upon. So the kind of impetus for this talk today is that in 2013, we finally kind of put together a comprehensive report of our Stream Team data that we've been collecting since 1998. So this was sort of the first time that we'd actually analyzed that data all together as sort of a big project. So for that project, so this report, the Malibu Creek Watershed Ecosystem on the Brink, we looked at 12 years of data, so it's basically like 1998 to 2010. So some of the stuff I'll show you today is actually a little more updated with some of the newer data. So in this report, we assessed the habitat, water quality, and biota of the Malibu Creek watershed. And today I'll just focus sort of on the biota aspect. And this report is on our website, healdabay.org. You can download it there if you're interested. So just to kind of give you some basics about the Malibu Creek watershed. So it drains into the Santa Monica Bay, like I said. So we're west of downtown Los Angeles, about 35 miles, and it's the second largest watershed that drains to the Santa Monica Bay. So the first largest is the Bayona Creek watershed, and then Malibu Creek watershed is the second largest, and it's about 110 square miles. And sort of the interesting thing about the Malibu Creek watershed is that there's quite a bit of open space in this watershed. So it's only about 25% developed. There's a lot of parkland, especially in comparison to like the Bayona Creek watershed, which is kind of the opposite. It's about 25% open space. So here's sort of an image of the Malibu Creek watershed land use. So another interesting thing about this watershed is that it's sort of bisected, or not quite but by the 101 freeway. So you can see in the upper watershed, you kind of have some nice open space. And then we have the 101 freeway and a fair amount of kind of residential and commercial development right around the 101, which I'm sure you can all imagine. And then we have a fair amount of open space again in the middle watershed, and then and sort of lower, and then we have Malibu, city of Malibu right here, so then some more development in the lower watershed. So just kind of an overview of the stream team, so our current projects. So we monitor water chemistry. So since 1998, we've been doing that pretty much every month for, all these years. Right now we're cutting back a little bit to only monitor 6 times a year at 12 sites. Bioassessment we're doing yearly at 4 to 12 sites, depending on kind of the year as well as flow or whether there's water there. And then just kind of a little teaser, I'm not going to talk about this today, we just did an interesting pilot project over this last summer looking at freshwater swimming holes in the Santa Monica Mountains and looking at water quality there. And this is a popular spot here in the rock pools in Malibu Creek State Park. So today I'm going to obviously talk about bioassessment, but just kind of obviously the water quality stuff is related. I'm not going to talk about our results really today. But like I said, we've been collecting data over the years, every month. So we collect data on fecal indicator bacteria, nutrients, pH, dissolved oxygen, turbidity, conductivity, temperature, and algae. So now that this map shows our monitoring sites. So I'm going to kind of show you them color-coded. And we've classified our monitoring sites into kind of 3 groups. So we have sites that we consider sort of high-quality sites, or sometimes I call them reference sites, which I know a lot of people probably don't like that word, but we call them that in the report. So they're not like technical reference sites that probably a lot of you are used to thinking about, but we're calling them sort of high-quality sites that they tend to be downstream from open space and have few impacts. So here in green are these high-quality sites. So you can see we've got some that are kind of in the upper watershed or upper tributaries. And then we also actually have some that are outside the Malibu Creek watershed. So in the black is Malibu Creek watershed, and then these red areas are other close by watersheds, and we've relied upon some sampling there as comparisons because there's very little development in these sub-watersheds or these small watersheds. So those are our high quality sites. In the orange we have sort of middle watershed sites is what we're calling them. So these are sites that are downstream of some development. They're also sort of middle in the watershed or middle in tributaries that feed into Malibu Creek. And then we also have our outlet sites. So these are either outlets of the tributaries into Malibu Creek or obviously the outlet of Malibu Creek itself into the ocean. So like I said, I'm not going to go over the water quality, water chemistry results today, but this data is all available on our website at Heal the Bay. So if you go to streamteam.healthebay.org, you can actually view, you can graph different parameters at different sites, and you can download all that data. So please check that out and let me know if you have any questions about that. And then kind of, when I talked about the goals of the stream team, I think for us it's always important to use this data to inform policy. So just to kind of give you a little idea of some of the things we do with our data. For instance, we frequently submit it to the Regional Water Quality Board when they're looking at updating the 303D list. So we've contributed to that, to volunteer monitors who helped get streams listed as being impaired. And just to give you an idea, Malibu Creek has a lot of impairments, so some of our data has contributed to those listings. Not all of them, and obviously other people have contributed as well. Okay, so I'm going to talk specifically about our bioassessment program now. So we've been doing this since 2000, and we started with the California Stream Bioassessment Protocol, and we're doing that twice a year, sometimes, I believe, for the most part, from 2000 to 2006. And then in 2008, we switched over to the swamp protocol. So we do that once a year now. We collect data on physical habitat as well as benthic membranes. So I think, I don't need to convince this audience, but benthic macroinvertebrates are a great way to get an overall picture of our stream health and stream condition. So again, we use our benthic macroinvertebrate data to generate the SoCal IBI score, so the Index of Biological Integrity. We're using, which is based on 7 metrics, and again, it's a scale from 0 to 100. And we can also, I'll talk about this later too, a score of 39 or lower indicates biological impairment. So that will come up again. And these are sort of the 5 categories of IBI scores. Okay, so these are some of our results from our IBI scores. So these are averages for our different sites. So I'll walk you through this a little bit because it's a lot of information here. But to start on the right side over here, we have a graph that's showing the average IBI scores for those 3 different categories of sites that I mentioned. So right here, we have it called reference or high quality sites. So you can see the IBI score is obviously quite a bit higher for those sites. And then our outlet and middle sites have pretty low IBI scores. So we see this kind of decrease in biological health as we go down the watershed, or increasing in development, which isn't really, shocking. The interesting thing to note, I think, is that the middle and outlet sites are very similar. So we see quite a bit of degradation happening between these reference or high quality sites, even as we go down to the middle watershed. And then over here in the table, I have all the sites listed out, as well as their average IBI score, what category that puts them in, and then the number of samples. So, and I've arranged them so that, the top one, this is Cold Creek. So this is our nicest stream in the area, and it's the samples are going from upper to mid to lower. So you can see here that we get this kind of decreased IBI score as we go down, and that's sort of true also for another tributary, Las Virgenes Creek. So we see a higher IBI score in the upper watershed, and then actually lowest sort of middle, and then it's still pretty bad as we go down. Malibu Creek itself, actually the averages are all the same, and here we already have a lot of tributaries coming in. There's a lot of impacts already to that system. And then I'm just highlighting here these kind of high quality sites. So again, this is just mirroring the data over here. But again, you can see that for our high quality sites, they all fall into this either good or fair categories. And then everything else is either poor or very poor. So this is just the same data basically on a map, so you can see it visually or sort of spatially. So here again, you can see the 5 different categories of IBI scores. So we don't have any excellent sites. We do have a couple of good sites, and again, that's sort of Upper Cold Creek, so we're in this high quality site that's downstream of very, either just open space and also downstream of not a lot. And then we also have a couple of good sites in our outside the watershed sites. And then we go into the fair category, which again are sort of upper watershed, in this case mid Cold Creek, and then another outside the watershed. We have poor and then very poor that are both in the middle and outlet sites. So the interesting thing is we see this variability between sites, but when we look within sites over time, we definitely see some variability, but for the most part, our sites are pretty stable over time. There's not a huge evidence of degradation over time or improvement over time. So this is showing the IBI scores over time for 5 sites. So here you can see, for instance, Upper Cold Creek, throughout the years, we definitely see some up and downs, but for the most part, they're staying fairly constant. So this shows that our good sites are staying pretty good for the most part, which is great, but our bad sites are staying bad, but I guess without any huge, restoration or major changes in the watershed, we wouldn't necessarily expect them to improve. So what we did then was to look at potential stressors that would be impacting our biological health. So previous research has shown that biological health is impacted by amount of development and impervious area. So what we did for each site, we calculated the amount of development as well as the amount of impervious area that was upstream from that site. So we did that by looking at land use maps, and for imperviousness, we looked at specifically at different types of land use and quantified each land use with its impervious factor, and then came up with a percent impervious area upstream from each site. And then we wanted to look at how that was related to our IBI scores. So this is just showing for our different sites here. I don't know if you made it, or if it's a little fuzzy, but it's showing the percent of imperviousness upstream from each site. So it's ranging basically from like 2% at the low end up to 20-something percent at the high end. So that's the amount of impervious area upstream from the sites. So like I said, we looked at both amount of just percent of development and then upstream from each site, and then looked at how it was related to IBI score. So over here in this graph, we have IBI score on the y-axis, percent developed area upstream from each site on the x-axis. So we graphed this, and we can see that there is a statistically significant relationship between these two variables. So we find that there's a negative relationship, kind of logarithmic relationship here. And then what we did also was we performed a multiple regression model where we looked at IBI score as being impacted by developed area, and then we also included some other factors in there that we thought would impact IBI score, such as year, the protocol that was used for that sampling, as well as when we sampled. So again, we find that this model explains about 68% of our variability in IBI score, and we see that the amount of developed area upstream from each site is a significant predictor of IBI score. So again, looking back at this graph on the left, we added in our best fit trend line, so this is just the invariant relationship between IBI and developed area. And then we added in a dashed line here. This is the level of impairment. So this is when your IBI score is 39. So we added in that dashed line and then looked at where that hit our best fit trend line, kind of estimate the amount of development that would trigger kind of potential levels of impairment. So here we found that for development, we found that it's crossing this line at 8.8% development. So it's a pretty low amount of development that is corresponding to impaired level of biology. So we did the same thing with percent impervious area. So again, it's very similar since obviously the two factors, or development and imperviousness, are related to each other. So we weren't surprised to see they were very similar. So again, we find that there's a nice relationship. We find that imperviousness, again, is a significant predictor of IBI score, taking into account all these other variables. And again, we looked at where that IBI line of 39 crosses our best fit trend line, and we found that in the case of imperviousness, it crosses at about 6.6% impervious area. So again, this indicates to us that a fairly low amount of development upstream from a site can kind of trigger negative biological impacts. So just kind of some conclusions from this part, and I'm going to talk a little bit next about some things we're working on now. But is that we find a fair amount of biological degradation in the watershed. So looking at these impacts from development and imperviousness, we can kind of advocate for limits on development and imperviousness in the watershed. And again, it's sort of a great way that we can specifically point to these numbers and say, maybe we should try to aim for this level of imperviousness in a watershed, and we can try to get there through low impact development ordinances, or also by through redevelopment ordinances, and aiming for this low amount of imperviousness. So what we hope to do in the future also is to continue to examine additional stressors, and then again look at the physical habitat data that we have collected and incorporate that in, as well as some of our water quality parameters. So again, just to tie this into our policy outcomes, So in terms of our benthic macroinvertebrate data, there was a recent TMDL that was used, or that came out to address the biological impairments in the Malibu Creek watershed. So we submitted our data to EPA, both the water chemistry and biological data, and these data were helpful and integral in terms of coming up with this TMDL. And basically, I think Cindy Lynn presented on this last year here, showing that nutrients and sediment were impairments or causes kind of for the biological impairments. And then they ended up in the TMDL setting lower limits for both of those pollutants. Okay. So I'm just really briefly going to talk now about some kind of new work that we're doing with our bug data. So again, we have collected bug data since 2000, so we have a lot of data and a lot of potential questions we could answer with that. So one of the interesting things that we're hoping to answer is some of the impacts of New Zealand mud snails in the watershed. So New Zealand mud snails are an invasive species. I'm sure everyone is probably familiar with them here. So they arrived in the Malibu Creek watershed in 2005. So we have some great data both before invasion as well as after invasion and in different streams. And they kind of invaded different years and different streams. So this is a map showing an invasion. I think this is old. They're found in about, I believe, 12 streams now in the Santa Monica Mountains, so not just Malibu Creek watershed, but they've spread quite a bit. So what we're doing, and this is kind of just a real preliminary analysis that we're working on now, is, so I did just a quick comparison of looking at IBI scores. So this is pre-New Zealand mud snail invasion and post-New Zealand mud snail invasion. And we actually do see a decrease. So we were always kind of worried about the IBI score not taking into account invasive species specifically, but maybe there actually is something going on here that we're seeing a decrease in the biological health potentially. So this, again, we're not taking into account, tons of other factors that might be impacting IBI, so this is just sort of a rough analysis, but kind of interesting. The other thing that we're looking at is specifically New Zealand mud snail abundance data from the different sites over the years. So some years, we have just tons and tons of New Zealand mud snails. You can see some of these numbers are almost, our whole sample is New Zealand mud snails. So we've been looking at that in terms of how they're impacting different taxa. So one interesting finding so far is that it appears that betas or mayflies are being negatively related to New Zealand mud snails. So we see more mayflies when New Zealand mud snails are either absent or very low numbers. So we want to keep looking into this as well as other taxa. Another just kind of interesting thing is to look at some of the metrics that are related and see how they're related to New Zealand mud snail abundance. So here this is showing Shannon Diversity Index on the y-axis and then New Zealand mud snail abundance. You can see this sort of negative relationship. And again, this is essentially a little circular because Shannon Diversity Index takes into account both your species number, evenness, and since we're kind of just, of course we're not going to have an even sample if we have 500 New Zealand mud snails when we're only sampling 500. But anyway, it's an interesting, at least starting to think about some of these things and how they're related. And then the final thing that I've looked at so far is just looking at, again, these different metrics, so like the different metrics that make up the IBI score. So one example here is looking at the percent of collector-gatherer individuals. So we're finding that there's a negative relationship here as New Zealand mud snail abundance increases. So again, these bugs, it's kind of determining the collector-gatherer individuals describes how they feed. So we think, we don't know all the reasons behind this, but potentially there's competition for either space or food or something. So we're trying to tease that out. So some future directions for this is, like I said, we're going to look at different taxa and how they're responding to New Zealand mud snails, both the abundance and also just kind of presence, absence, or pre and post invasion. And then also look at other explanatory variables such as water quality, differences among the sites, rainfall, and things like that. And then we're also just starting up a project to look at the impacts of invasive red swamp crayfish on Benedict macroinvertebrate communities, which I think will be interesting as well. And I think that's it. So I just want to thank everyone, all the partners we had, all the volunteers, obviously, as well as Jim for inviting me out here. Thanks.